Imagine boarding a plane in New York and stepping off in Beijing less than 2 hours later, faster than your current commute to work. This is not science fiction, nor the plot of a futuristic film. It's the promise of a radical new leap in aerospace innovation, and China is leading the charge. At the center of this technological revolution is the Nanchang No. 1, Hypersonic Travel, a hypersonic aircraft designed to fly at speeds exceeding Mach 6, nearly 7,400 km per hour. With the potential to transform global travel, military strategy, and even space access, this next-generation aircraft represents far more than just speed. Today, we'll unveil how this new Chinese plane will change travel forever. Let's get started. Hypersonic travel to become a reality. Hypersonic travel is set to redefine the future of global aviation by making journeys at speeds exceeding Mach 5, over 3,800 miles per hour, not only feasible but potentially routine. This leap in technology opens the door to point-to-space travel, where aircraft briefly exit the atmosphere before re-entering and gliding toward their destination. Such advances could compress intercontinental flights into a matter of minutes. For example, routes like New York to Beijing, which currently take around 14 hours, could be completed in less than 2. China is actively pursuing this vision with striking momentum. Back in 2023, China conducted a successful test flight of Nanchang No. 1, an experimental aircraft. During its trial run, the jet reached speeds of Mach 6, approximately 4,600 miles per hour, marking a major technical breakthrough. At these velocities, conventional aircraft design is insufficient. The Nanchang platform incorporates advanced heat-resistant materials and high-performance propulsion technologies capable of enduring the intense friction and pressure associated with hypersonic travel. Hypersonic aircraft require complex propulsion systems that differ significantly from traditional jet engines. While commercial planes rely on turbofan engines that perform well at subsonic speeds, hypersonic craft use a combination of turbofans, ramjets, and rocket engines. Turbofans provide the thrust for initial takeoff and low-speed flight. As velocity increases, ramjets take over, utilizing compressed incoming air to generate combustion without moving parts. For the final acceleration beyond Mach 5, rocket engines are engaged, offering the raw power needed to sustain hypersonic speeds. This layered propulsion approach enables aircraft to smoothly transition through varying aerodynamic conditions from ground level to near space. China's aggressive investment in hypersonic research is not limited to civilian travel. It is part of a broader aerospace strategy that includes national defense and space exploration. As global powers race to master this transformative technology, hypersonic flight is becoming a critical arena for innovation, geopolitics, and the reimagining of global mobility. Let's break down the components one at a time. Engine technology and challenges. Propulsion. One of the most cutting-edge propulsion systems under development for next-generation hypersonic vehicles is the multi-ducted twin-turbine ejector ramjet, more commonly referred to as the Mutter engine. This complex hybrid engine blends the functionalities of multiple propulsion technologies, namely turbofan, ramjet, and rocket systems, into a unified design capable of powering aircraft to speeds reaching and exceeding Mach 6. The challenge of accelerating smoothly across such a wide speed range, from a standstill to hypersonic velocities, requires a multi-stage approach that adjusts propulsion mechanisms in response to changing aerodynamic conditions throughout flight. At takeoff and during the initial climb, the aircraft depends on traditional turbofan engines. These engines, familiar from commercial aviation, use a fan-driven system to compress air, mix it with fuel, and ignite the mixture to produce thrust. They are highly efficient at subsonic speeds, offering stable performance during the early phases of flight. However, once the aircraft surpasses the sound barrier, rising drag and air resistance begin to limit the turbofan's efficiency. At this point, ramjet technology becomes essential. Ramjets, unlike turbofans, have no moving parts and rely on the aircraft's velocity to compress incoming air. This compressed air is mixed with fuel and ignited in a combustion chamber, producing thrust that is ideal for supersonic and lower-end hypersonic flight. The Mutter engine enhances this process with additional ducts and ejectors that improve airflow management. This helps prevent flow separation and pressure instability. Ramjets typically operate most effectively between Mach 3 and Mach 6, but pushing further into the hypersonic regime introduces major challenges in combustion control and thermal dynamics. For velocities beyond Mach 6 or operations near the edge of Earth's atmosphere, rocket propulsion becomes indispensable. Rocket engines differ fundamentally from air-breathing systems by carrying both fuel and oxidizer, enabling thrust even in oxygen-deprived environments. This makes them critical for high-altitude or near-space phases of hypersonic flight. Historic platforms like NASA's X-15 and the Space Shuttle demonstrated how rockets could deliver massive thrust at the upper limits of speed and altitude. The Mutter engine's architecture may integrate rocket modules for the final boost, allowing the aircraft to sustain stable hypersonic cruise or execute high-speed re-entry trajectories. Cooling thermal management is arguably the most formidable technical barrier in hypersonic propulsion. At speeds above Mach 6, surface temperatures on the aircraft can soar beyond 2000 degrees Celsius due to atmospheric friction and shock wave compression. To counteract this, developers rely on a combination of heat-resistant materials and active cooling methods. Advanced composites such as carbon-carbon, used in NASA's X-43A, offer extreme thermal resilience, while liquid-cooled engine components and ceramic coatings help protect internal systems from heat damage. Elements of re-entry technology, originally devised for spacecraft returning from orbit, are now being adapted to stabilize engine performance under these conditions. As testing continues and materials science advances, hybrid systems like this could soon bridge the gap between aviation and spaceflight, making rapid global transit and low-orbit missions increasingly viable. Unmanned prototype aircraft have been instrumental in advancing hypersonic flight research, serving as essential platforms for testing the extreme physical and engineering challenges posed by sustained speeds above Mach 5. These early-stage test vehicles are specifically built to endure and replicate the intense conditions that define hypersonic travel, where atmospheric friction, aerodynamic stress, and thermal loads converge at unprecedented levels. As noted earlier, a scaled prototype of China's Nanchang No. 1 achieved a controlled flight at Mach 5.8 in 2023. This test not only confirmed the reliability of the multi-stage propulsion architecture but also validated the materials and heat management strategies needed to survive prolonged exposure to extreme temperatures and pressures. These unmanned experiments were designed to push each system to its limit, ensuring that the aircraft structure, guidance algorithms, and engine components could withstand the punishing demands of hypersonic operation. The outcomes were overwhelmingly encouraging, indicating a strong technological foundation from which full-scale development could proceed. China now appears poised to launch the operational phase of its hypersonic program. But several issues must be addressed first. Handling noise pollution. When an aircraft travels faster than the speed of sound, or Mach 1, it generates shock waves that converge into a powerful, thunder-like sound known as a sonic boom. This phenomenon, long associated with supersonic jets like the Concorde, is expected to intensify as aircraft begin operating at hypersonic speeds exceeding Mach 5. The underlying physics remains unchanged: faster aircraft produce stronger shock waves, and stronger shock waves mean louder, more far-reaching booms. For communities situated beneath these flight paths, that translates to significant noise disturbances. Historically, this issue has had tangible consequences. The Concorde, which cruised at around Mach 2, was infamous for its loud sonic boom. In many parts of the world, especially the United States, overland flights were prohibited due to the noise's disruptive impact on residential areas. The aircraft was restricted primarily to transatlantic routes, flying over oceans to avoid populated zones. Despite its technological sophistication, this limitation severely hampered the Concorde's commercial viability. Hypersonic jets, which will fly even faster and produce more intense shock waves, risk facing even greater restrictions unless a viable solution to the sonic boom problem is developed. One of the most promising efforts to tackle this issue comes from NASA's Quiet Supersonic Technology or QSST initiative, particularly through the development of the X-59 experimental aircraft. Designed to reshape the way shock waves form and propagate, the X-59 features an elongated fuselage, a sharp, narrow nose, and a specially tailored wing configuration intended to spread out shock waves rather than allowing them to merge into a loud boom. The goal is to transform the traditional sonic boom into something closer to a muted thump that would be far less disruptive. However, translating this research into practical, widespread application, especially for hypersonic speeds, is far from straightforward. The X-59 is still in the testing phase and is built for lower supersonic speeds, not the much higher thresholds that hypersonic aircraft will reach. Scaling up these noise reduction technologies to work at Mach 5 and above presents major engineering challenges, especially as shockwave strength increases exponentially with speed. Even if breakthroughs are achieved, implementing such innovations across a fleet of commercial hypersonic jets would require standardization, rigorous safety assessments, and adherence to stringent regulatory frameworks. Regulatory hurdles are already in place, with agencies like the Federal Aviation Administration currently enforcing bans on civilian supersonic travel over land. If hypersonic jets generate even louder booms, these regulations may tighten further. This poses a direct threat to the economic feasibility of hypersonic commercial travel, which depends on high-frequency, point-to-point routes often spanning major landmasses. If aircraft are restricted to over-water paths, many lucrative city-pair connections, such as Los Angeles to Chicago or London to Berlin, would be off-limits, narrowing the market and reducing profitability. Without meaningful advances in noise suppression, this revolutionary mode of transport may be grounded by the very regulations designed to protect communities from its thunderous roar. But wait, the concerns don't end here. What about the heat? At hypersonic velocities, where aircraft exceed speeds of 3,800 miles per hour, the surrounding air becomes a punishing environment. Even before it makes contact with the vehicle's surface, the air is compressed and superheated, generating an intense envelope of thermal energy. The result is a relentless rise in skin temperatures that can exceed 2,500 degrees Celsius, a level of heat far surpassing that encountered by conventional supersonic aircraft and even spacecraft during atmospheric re-entry. To put it in perspective, the Space Shuttle platform experienced peak re-entry temperatures around 1,500 degrees Celsius. This continuous heat buildup doesn't merely graze the outer shell. It permeates into the core of the airframe, placing immense stress on structural components, fuel systems, and internal electronics. If not properly managed, this thermal onslaught can weaken alloys, cause materials to deform or melt, and compromise the aircraft's structural integrity. The challenges faced during the development of the Boeing X-51 Waverider highlighted this risk. During flight tests at Mach 5, heat buildup threatened to exceed material tolerances, prompting engineers to rethink not only surface coatings but the very structural makeup of the craft. It was through these lessons that the importance of high-temperature materials, particularly ceramic matrix composites or CMCs, became evident. CMCs combine the heat resistance of ceramics with fiber reinforcement to maintain strength at extreme temperatures, making them ideal for components exposed to the most punishing thermal conditions. Yet passive defenses like CMCs and reflective coatings only go so far. Thermal management hypersonic flight isn't a brief, high-heat spike. It is a prolonged, thermally aggressive journey. Spacecraft are designed to withstand short-duration heating during re-entry, but hypersonic aircraft must manage heat for the entirety of their flight path. Traditional cooling systems, such as airflow-based or liquid-cooled solutions used in supersonic jets, fall short at these scales. As a result, active thermal management has become a necessity. One widely studied method is regenerative fuel cooling, where the aircraft's fuel is circulated around critical hot zones, such as leading edges or engine components, absorbing heat before being injected into the combustion chamber. This dual-purpose approach serves both as a heat sink and a preparatory phase for combustion, increasing fuel efficiency while preserving structural safety. Managing temperature gradients also becomes a complex task, as shifts in altitude, velocity, and air density can create uneven heating across the aircraft's surface. Localized thermal spikes can lead to warping, surface erosion, or failure in control surfaces, each a potential trigger for in-flight instability or loss of control. The interior is just as vulnerable. At hypersonic speeds, avionics, navigation hardware, propulsion management systems, and onboard sensors are all at risk of overheating. While military jets already rely on ruggedized semiconductors and liquid-cooled avionics bays, hypersonic conditions demand an entirely new level of heat mitigation. Prolonged exposure to high temperatures can cause system lag, sensor distortion, or complete failure in communication and guidance systems. To address this, researchers are developing microscale heat transfer solutions, including embedded heat pipes that operate through capillary action to draw heat away from sensitive electronics. These systems offer a passive, compact, and energy-efficient way to safeguard mission-critical components. While still in development, they represent a forward-looking approach to solving the internal heat dilemma. Without a robust and multi-layered thermal protection strategy, one that combines advanced materials, active cooling, and intelligent thermal routing, no aircraft can survive the journey at Mach 5 and beyond. This is not all, though. Further challenges to be addressed. While the allure of cruising at Mach 5 and beyond captures the imagination, the technological demands required to sustain hypersonic speeds impose severe limitations on aircraft size and passenger capacity. Unlike traditional airliners, which are designed for volume and comfort, hypersonic vehicles are meticulously engineered to optimize speed, stability, and survivability in one of the harshest flight environments imaginable. Most experimental and conceptual designs today can seat fewer than 10 passengers. You see, every kilogram onboard a hypersonic aircraft must justify its presence. Lightweight materials like ceramic matrix composites and titanium alloys are used not just for their strength, but for their ability to withstand blistering temperatures and shear forces. But these materials are expensive and often space-limiting. Adding more seats increases internal volume, which in turn increases drag, surface area, and overall weight, three interdependent variables that directly reduce the aircraft's efficiency and structural integrity at high speeds. A larger fuselage also invites complications in airflow management, potentially destabilizing the aircraft at Mach 5 and above. Thermal protection remains the most pressing challenge when scaling up. At hypersonic speeds, skin temperatures rise exponentially with surface area. Enlarging the aircraft means exponentially more heat buildup, requiring correspondingly more elaborate cooling systems, whether passive shields, regenerative fuel circuits, or active heat dissipation systems. These additions introduce new structural and operational complexities that not only increase cost but diminish the speed advantage that hypersonic travel promises in the first place.